Hello class, this is a video for section 6.3 and 6.4. 6.3, test for a single proportion. Um, so, to compute a hypothesis test for a single proportion, we need a couple quantities. We need the proportion as suggested by the null hypothesis, the sample proportion, and the sample size, and of course some hypotheses to test. The normal distribution calculator will do most of these calculations for us. Let's see an example. Example 6.7 in the book is regarding the approval rating of Congress. So the null hypothesis states that the approval rating is 20%, and the alternate is that the approval rating is less than 20%. Out of 1,013 people sampled, 19% of them approved of Congress. Now 19 is certainly less than the null hypothesis claim of 20, but it's not that much less, and since it's a sample proportion, there's some randomness involved. We want to know if this is low enough to actually support the alternate hypothesis, or if this is just a random sample. Note that because the alternate hypothesis says that the proportion should be less than 20%, that this is a left-tailed alternative. Let's see how the advanced normal distribution calculator will compute our p-value for us. Now, we are computing a hypothesis test for proportion without bootstrapping using the central limit theorem. And the information is here. So the null hypothesis proportion is 20%, the sample proportion is 19%, and the sample size is 1,013. And again, we have a left extreme, and that gives us about 21%, which is exactly what the book states. The book has a slightly different number. We used slightly different approximation techniques. 20% p-value is larger than any reasonable level of significance, so we can't conclude the approval rating is less than 20% for our sample. And hence we support the null hypothesis. The approval rating is 20%. Section 6.4, distribution of a sample mean. The upshot here is that standard error is computed by sigma over the square root of n, and that the larger the sample size is, the smaller the standard error is for our sampling distribution. We're going to use this to compute hypothesis tests and confidence intervals. Because of the central limit theorem, we don't need to use randomization techniques or anything like that. We can just use the normal distribution, or we'll see momentarily the t-distribution. There are certain technical restrictions, namely that the sample size should be larger than 30 when applying the central limit theorem. Let's look at an example. This is example 6.10 in the book, regarding the mean income of statisticians. That's provided by the Bureau of Labor Statistics, and its mean is $75,220 with a standard deviation of $32,000. We're going to assume all of these are parameters. The distribution of sample mean salaries of 100 randomly selected statisticians would be approximately normal, with a mean of 75,200 and a standard deviation of 3,200. The distribution of sample means for 400 randomly selected statisticians would be approximately normal, with 75,200 as the mean and 1,600 as the standard deviation. Let's see what that means in the advanced normal distribution calculator. Reading confidence intervals for the mean, we enter in all the information here, and I switched my level of confidence to 0 since we're not really worried about that. But notice that it's a normal distribution centered around 75,200. And And look what happens as we increase the sample size. Again, increasing the sample size should reduce our standard error, which should reduce our spread. So watch how the scale changes when I hit enter here. The scale goes down, the spread is lowered as I increase sample size. Let's increase it some more. It goes down even further. The larger the sample size, the less variation in our results. Now, if we don't have the true standard deviation, we want a technique where we can just use the sample standard deviation. In this case, we modify our method, and instead of using sigma, we use S here. But that means our distribution will change since we know a little bit less. And that's what we call the t-distribution. This is similar to a normal distribution, and we use it when we don't know the true standard deviation. It's based on sample size. It, loosely speaking, has fatter tails, which means the confidence intervals we generate using the t-distribution are wider. We get larger p-values. We say this is formally the name is the t-distribution with n minus 1 degrees of freedom, where n is the sample size. And we use this for means primarily, but not proportions, because standard error is not independent of p in the proportion case. One other thing to note is the larger the sample size, the closer it's approximated by the standard normal. And when your sample size is like above 150, it's not really much different, and we can kind of use them interchangeably. But if we have a low degrees of freedom, low sample size, this is kind of what it looks like. In red is normal, in blue is the t-distribution, and as I said, it has fatter tails. It'll produce a larger confidence intervals and so on. That's it for section 6.3 and 6.4. 6.5 and 6.6 will come soon.